All right, class, let's go ahead and jump right into the equilibrium constant and what role it plays in looking at equilibriums. So when you have a reaction, you have a forward direction for the reaction, and you can determine the rate law of that forward reaction. So you have the rate equals the forward rate constant times the concentration of N2O4. But you also have a reverse reaction, okay, and it would have its own rate law as well. So the rate is equal to the rate constant times the concentration of the NO2, and that'd be squared because of the coefficient. So therefore, at equilibrium, when rate F and rate R are equal to each other, because they're going to be equal to each other if they're at equilibrium, you can put the relationship that both equations are together. So then if we kind of move things around algebraically, we get this relationship of the two rate constants there, and then we have this relationship of the concentration of the products over the concentration of the reactants. Okay, and then obviously we have that superscript that's squared because the coefficient in front of the NO2 is a 2. Okay, so actually let me double check something real quick because I may have just totally misspoke. I did misspeak. Okay, so with the rate, so we have the reactants on the top, products on the bottom. Okay, sorry about that. All right, so the ratio of the rate constants is a constant. So, I mean, if you have a constant divided by a constant, it's just going to be another constant, right? So we change the name rather than calling it the forward constant over the reverse constant. We just make it a new constant, and that constant is the equilibrium constant in this case. And you could write them for any equilibrium equation, where you're basically writing the reactants on the top using their coefficients as the superscripts, and then the products on the bottom. And you would also, if there was coefficients with the products, you would include those as superscripts as well. So let's generalize it. So we have an equation all the lowercase letters represent coefficients, and all the uppercase letters represent the compounds that are involved in this relationship. So a general equilibrium expression would be where you've got, oh, see, I was right. What the heck? I'm confusing myself. Dang it. I apologize. So your products are on the top with our coefficients as the superscripts. Jeez, I knew I was right when I said, anyway. And then your reactants are on the bottom with the coefficients turning into the superscripts for the reaction. So use this, not what I said, but what I now say. Sorry. Okay. Next, you have, when we talk about equilibrium constant, you can also relate it to the pressure of a gas, because really the pressure of a gas and how much of a gas is basically the same thing. So, since pressure is proportional to concentration for gases in a closed system, the equilibrium expression can also be written this way. So, like the equilibrium constant for a reaction where all of the components are in the gas phase would just be your products on the top and reactants on the bottom, and using pressures rather than concentrations. So if we manipulated, okay, if we took the ideal gas equation where pressure is equal to N over V times RT, we can plug that into the expression for Kp for each substance, and the relationship between Kc and Kp, or the equilibrium constant for the reaction, is related to the equilibrium constant of the pressure of the gas. Okay, so equilibrium can be reached from either direction. So this, you've got 4 different experiments that are represented in this table here. And you see that the equilibrium constant is pretty much the same, but we have different concentrations, different starting amounts for these different compounds. When we get at equilibrium, they go to kind of a final amount. And this, obviously, this table is in your textbook as well. So the ratio of the concentration of NO2 squared to N2O4 remains constant at this temperature no matter what the initial concentration or the NO2 and N2O4 are. So the ratio stays the same throughout, and that's really kind of the main idea of equilibrium. So this is the data from the last two trials on that table, and you'll notice, so in experiment 3, you started with 0.04 moles of the material, and I forget what in experiment 4 you had 0.02 moles of this NO2 or N2O4 and none of the NO2. That's the kind of the marker indicated there. But they eventually meet at the same equilibrium point. So it doesn't matter whether we start with N2, so different reaction, but so it doesn't matter whether we start with N2 and H2 or whether we start with NH3, so this is the production of ammonia. We will have the same proportions of all three substances at equilibrium. That's just the, and so really, depending on what your starting materials are, it determines which direction your reaction will go. So if you start with all reactants, then the reaction will go in the forward direction until it reaches equilibrium. Now let's say you start with all products, then the reaction is going to move in the direction of the reactants, so in the reverse direction until they reach equilibrium. So what does the value of K mean? Okay, so let's say we have a K that is much greater than 1. Then that means that the reaction favors the product. So things tend towards, when things reach equilibrium, you're going to have far more products than reactants. Now if your K value is lower than 1, then the reaction favors the reactants, and so you're going to have more reactants than products in the end as far as at equilibrium. So how can we manipulate the equilibrium constant? So let's say, so the equilibrium constant of a reaction in the reverse reaction is the reciprocal of the equilibrium constant of the forward reaction. So if we have that in the forward direction, the equilibrium constant is 0.212, then if we reverse the reaction, if we write it the other way, then the equilibrium constant is the inverse of it. So basically, easiest way to do that is take 1 and divide it by the equilibrium constant for the first reaction, and you get the equilibrium constant for the second, or for the reverse reaction, writing it the other way. So the equilibrium constant of a reaction that has been manipulated by a number is the equilibrium constant raised to a power that is equal to that number. So let's say the whole reaction, so you notice with the first reaction it's the coefficient is a 1 and a 2. And so the equilibrium constant is 0.212. The second reaction is 2, has a coefficient of 2, but then a coefficient of 4. So everything's been doubled in this reaction. And so what happens to the equilibrium constant is that it is squared. Okay, so since the numbers were doubled, the equilibrium constant would be squared. Let's say all the numbers were tripled. Okay, then we would cube the equilibrium constant. The equilibrium constant for a net reaction made up of 2 or more steps is the product of the equilibrium constants for the individual steps. And this is the idea that let's say you have a multi-step reaction, and each one of those steps has an equilibrium constant. So it's a dynamic reaction. So what you can do is you can actually add those steps together to find so just like we might add 2 equations together, and let's say there was a slow step and a fast step, like we were looking at in chapter 14 with kinetics. Well, then we would have a 2 equations, and we add them together to find, what are we starting with, what are we ending with, our final total equation. Well, we can also add together those equilibrium constants. And this is something that we're going to need to do as probably as a class as we work on equations, but that's it for today. Those were sections 3 and 4. I forgot to go through section 3 or 2, sorry. That was sections 2 and 3. Forgot to go through section 2 in last night's lecture. So you got a bit of what the problems you were working on today are in this lecture. And then tomorrow's stuff is section 3 stuff. So with that, have a great weekend, and I'll pop in and say hello on Monday.